do you contain the uncontainable?
Oh my God, there it is. There's a tornado right there.
They are the most violent winds known to mankind, swirling to the ground at more than 300 miles per hour and destroying virtually everything in their path. And yet, science and technology is casting its net to make order from this terrifying chaos. From satellites in space to advanced radars on the ground, the chase has begun. There is little in nature more violent than the explosive destruction of a tornado as it strikes the Earth's surface.
Oh my God, I know it.
1,000 of these ferocious windstorms strike the United States each year, killing about 50 people. But in the past, the annual death toll often reached hundreds. For generations, the terror left behind by these monstrous storms came not only from the devastation, but from fear of the unknown. Today, weathercasters can warn people an average of 11 minutes before a tornado is likely to strike. But once, there was no notice at all. The lucky ones caught sight of an approaching tornado in just enough time to seek shelter. But understanding and predicting tornadoes has been an ongoing scientific quest, achieving steady progress for the last half-century.
Our understanding of tornadoes has advanced amazingly in the last 50 years. We're right now at the point where we can identify the conditions that are likely to produce the most significant tornadoes fairly well and fairly far in advance.
Scientists believe the cause of tornadoes begins with wind shear, which results from winds at different heights blowing either at different speeds or from different directions. Wind shear produces horizontal rotation. Most tornadoes in the U.S. form in the spring when masses of cool, dry air from the north meet warm, moist air from the Gulf of Mexico. The warm air rises, creating a powerful updraft, along with clouds reaching up to 10 miles high. If wind shear rotation is present, the updraft tilts it from horizontal to vertical. The result is a supercell, a towering thunderstorm with a strong region of rotation 2 to 6 miles wide. This large rotation is called a mesocyclone, an important word to tornado forecasters. Unfortunately, it isn't known just how a mesocyclone turns into a tornado. It is a serious gap in the current science.
We are entirely incapable of predicting exactly what storm will produce a tornado and if a storm will produce a tornado or not.
Technology has been in pursuit of the tornado's mysteries for more than a century. In 1884, when still cameras were considered high-tech, the first photographs of tornadoes were taken. Motion pictures of a tornado didn't appear until a movie camera recorded these scenes near the town of Corn, Oklahoma in 1951. Today, the primary tool for peering into the depths of the tornado is radar. With their gleaming white protective domes, these modern installations are a far cry from their crude ancestors. World War II technicians always knew they could see storms on their scopes. But in 1947, the Air Force's Thunderstorm project used radar to study weather systematically for the first time. In 1953, the first Hook echo appeared on weather radar at the Illinois State Water Survey. Forecasters would learn to recognize this as a sign of a possible tornado.
And there's a hook-like shape in the reflectivity.
Today's multicolored radar displays may look different from their predecessors, but the principle of the system is the same. Transmission antennas send out beams of radio waves, and if they strike raindrops or hailstones, the waves are bounced back.
In this particular image, what we're seeing is the colors of green and yellow and red represent the intensity of rainfall and hail that's occurring.
In In 1973, radar technology took a leap forward as the National Severe Storms Laboratory built its first experimental Doppler radar. Doppler is different from conventional radar because it not only measures the amount of rain, it also measures the speed and direction of winds in a storm, something the old radars could not do. Doppler radars today have two different kinds of displays. One is a reflectivity display, showing the simple location and intensity of rain. The other is a velocity display, showing the speeds of winds in a storm.
What we see here is an area of very strong or bright green colors, and those are winds that are flowing strongly toward the radar. Next to that is an area of red, where the winds are flowing away from the radar.
Color codes on the radar display give us a clue to the shape of the storm. Doppler radar works like a police officer's radar gun and measures wind speeds coming toward or going away from the antenna dish. If a storm has a strong circular motion, it will show up on the display as a color couplet. Like the hook echo, the Doppler couplet is another telltale clue for tornado forecasters.
So what we have is a counterclockwise circulation within the updraft region of this thunderstorm that's approaching Oklahoma City. And this is precisely the type of feature called a mesocyclone that we look for when we're trying to identify storms that have a tornado potential.
Doppler radars physically rotate their dishes constantly so they can scan large areas with their beams. 158 weather Dopplers are scattered across the country, all connected in a network called NEXRAD, for Next Generation Radar. Completed in 1995, NEXRAD teams with advanced weather satellites to give us a complete view of the forces that produce tornadoes.
This one's going to go tornado. That one right there is probably ready to go. I mean, it just looks so favorable down there. So that's pretty much it.
This is the Storm Prediction Center in Norman, Oklahoma, where the process of tornado prediction starts. The people in this small room look at the big picture, watching the weather across the whole country.
Our job is to forecast where storms are going to be before they form.
This is where forecasters may put out a tornado watch, which means tornadoes are possible and people should be on the alert for more warnings to come. Here, one of the most important tools is the current generation of weather satellites.
Satellite data 30, 40 years ago was very crude, and sometimes what we would do is we'd only get one picture a day on a facsimile chart. Today, we have such an integrated picture with satellite pictures that are so clear and so detailed that it makes it easier to identify environments and weather patterns that can produce areas of severe weather.
While the Storm Prediction Center watches the whole country, local and regional conditions are monitored by more than 100 local offices of the National Weather Service. Here, detection of things such as thunderstorms with mesocyclones result in tornado warnings, which means tornadoes are imminent. The future of tornado technology presently resides in a concrete dome not far from the Severe Storm Lab's original 1973 experimental Doppler dish, now retired and on public display. The new dome houses the flat-faced antenna of the innovative phased array radar, which might replace NEXRAD in 15 or 20 years. Instead of scanning the sky slowly by rotating the dish, this radar plots its fast-moving beam without moving parts electronically. A scan taking 6 minutes today will take less than 1 minute in the future, improving tornado warning times dramatically.
Warning lead times today are around 11 minutes, okay, on average across the country. We're hoping to increase that to around 22 minutes.
But how will those quicker warnings reach the public? For that, the government forecasters largely depend on a proven technology, television. You are watching Nature Tech Tornadoes here on the History Channel.
Built tough and ready to brawl, big rigs of combat tonight.
On the eve of any war, 3 things must be considered.
How? In what History Channel?
You are watching Nature Tech Tornadoes here on the History Channel. When the Storm Prediction Center, or National Weather Service, issues a tornado watch or warning, it goes out over the automated National Oceanic and Atmospheric Administration radio network. Special NOAA weather radios receive the signals and are commonly purchased by people who live in tornado-prone areas.
Yeah, Val, we need you to head north on I-35.
But much more of the responsibility for getting the word out ends up in the hands of commercial broadcasters.
In Oklahoma, and I'm sure it's true elsewhere, television and radio are basically the source for weather information to the public. The National Weather Service responsibility is get the information out to the media, and we in turn get it to the public.
Gary England is the chief meteorologist at Channel 9 KWTV Oklahoma City, in the heart of tornado country. Mike Armstrong is a junior member of the staff. Outside the studio is the station's own unique Doppler radar dome. Tornado technology with a different twist than the government's NEXRAD system.
The main difference between our Doppler system and NEXRAD is that ours is real time. With NEXRAD, you have to wait sometimes between 6 to 10 minutes to get a full picture of what's going on.
TV radars are able to work faster because they cover smaller areas than the national NEXRAD system.
I've got a tornado emergency. Let's break immediately.
Gary England has been on the weather beat at Channel 9 since 1972 and was instrumental in bringing advanced hardware to the station. The nation's first TV weather radar was installed here in 1973. In 1981, KWTV erected the first operational weather Doppler radar anywhere, at a time when it was still experimental at the National Weather Service. And the first ever Doppler tornado warning went out in March of 1982.
Okay, we're on Doppler now, and this is a storm near Kanawha, Oklahoma, and does indicate a mesocyclone, and there has been a tornado sighted with it earlier. And also, this is the hook echo right here. And we can see the tornado itself. This is the actual tornado, and you notice as it moves around, it morphs and changes.
Today, Doppler radar remains at the heart of tornado technology here. But updated computer software offers a much more detailed picture than ever before.
The newest system we have right now really doesn't have a name. We sometimes call it M9. We sometimes call it MOAR, for Mother of All Radars. It's getting ready to come right over our station at this particular time. The eye of it passes directly over us. Fortunately, it was in the air.
In early May 2003, during a record outbreak, the MOAR radar showed one tornado uncomfortably close to the station. Outside, it was seen by Val Castor, a station crew member called a storm tracker, equipped with a camera and sent out to spot tornadoes. This one was headed directly for the KWTV building.
Val, are you saying it's over the television station?
Yes, I'm saying it's right over Channel 9.
Get people out of this studio. Get them out of the studio.
Here, guys, come on.
The station staff rushed to the interior of the building, where they'd be the safest. They were lucky that the funnel cloud remained above the station and did not touch down. As they heard reports coming in from storm trackers, the role of human eyes in the technology web became alarmingly clear.
There's no radar in existence that can tell you if a tornado's on the ground. It's so important to have people in the field for ground truth.
This was the picture that I actually took on May 3rd, 1999. It was the first tornado, first ground shot of any tornado to hit the air in Oklahoma City on this day.
Mike Armstrong worked in the field as a storm tracker for the station in 1999 when a massive tornado struck Moore, Oklahoma, just south of Oklahoma City. When all was said and done, damage from the superstorm totaled $1.2 billion. more than any other tornado in history. Without question, this was considered an F5 tornado using the Fujita scale, which applies the science of numbers to the damage that tornadoes cause. Developed by Professor Ted Fujita in 1971, the scale estimates a tornado's wind speed from the damage it leaves behind. F0 tornadoes do little damage, with winds under 73 miles per hour. At F5, structures are obliterated by winds as high as 318 miles per hour. Mike Armstrong's still photo of the big tornado headed toward Oklahoma City in 1999 reminds us how quickly advanced technology evolves. The photo was transmitted by cell phone.
In 1999, that was unheard of. Now you have all these different cell phone companies that give you the option of sending pictures of your friends and family and dogs and cats or anything else for that matter. But at that time, basically no one had that capability really except for people that were in the field using that technology at the time.
But others in the field had a different mission.
Not sure how strong it is, still looking pretty big.
When scientists took radar on the road that day in 1999, they could never guess they'd measure the most powerful tornado winds ever recorded.
Sam, that's a monster.
You are watching Nature Tech Tornadoes here on the History Channel.
I'm terribly sorry. We seem to have overbooked. We do have one room left.
Nature Tech Tornadoes here on the History Channel. Each year during tornado season, you can see truck-mounted radars hitting the road in Norman, Oklahoma. They are deployed by several different research teams, jointly run by the University of Oklahoma, the National Severe Storms Laboratory, as well as institutions as far away as the University of Massachusetts. The radar trucks do what the NEXRAD system cannot. Instead of waiting for the storm to come to the radar, they take the radar to the storm.
What that lets us do is see very fine-scale details. It's as if we're seeing the fingerprints on someone's hand from close up, as opposed to looking at that hand from across a parking lot.
Man, that thing is huge.
The need to get close to a tornado turns scientists into storm chasers. Researchers have been seriously chasing storms since the early 1970s, but pursuing them with effective radars is more recent. In 1995, the first Doppler on wheels, or Dow trucks, were deployed as part of Project Vortex, a large-scale study to examine the origins of tornado rotation. Josh Werman runs the Dow program.
We learned a lot about tornadoes and about tornado structures in Vortex. What we're still trying to learn are the harder questions of exactly how tornadoes form, of how we can distinguish between supercell thunderstorms that are violently rotating from those very similar storms that actually form tornadoes.
Scientists have long known that a tornado is a violently rotating column of air touching the ground from a thunderstorm. We used to be taught that tornadoes were akin to gigantic vacuum cleaners, capable of lifting trees out of the ground and houses off their foundations. Research in the field has shown that to be a myth.
The major element of a tornado, the major property of a tornado, is its very strong rotation. So mainly a tornado blows, doesn't suck.
But little is known about how tornadoes work, and only now is technology allowing scientists to look inside them. Determining the structure within a tornado is crucial to discovering how tornadoes form, a process called tornadogenesis that is still poorly understood.
Hi, how are you, Kate? Oh, my God. Sam, that's a monster. That's very blessed. Yeah, I hope this doesn't go to Oklahoma City. It's going to be strong. Well,
In 1999, the Dows encountered a massive tornado just outside Oklahoma City. It was, in fact, the very same storm photographed by KWTV spotter Mike Armstrong. No one who saw it could ever forget it.
We were able to stop a few times as it was coming towards Oklahoma City. It was a very dramatic thing visually. When we scanned into that storm, we saw alarmingly high wind speeds of about 135 meters per second, which is 301 miles an hour. Plus or minus. That's probably plus or minus about 20 miles an hour. But those were the highest wind speeds that anybody had ever measured anywhere, either in the jet stream or in a tornado or a hurricane, anything like that.
Another chase team, led by Professor Howard Bluestein, uses a special high-frequency radar to detect the smallest details of storms. They also encountered the massive 1999 tornado headed toward Oklahoma City, and in their fine-scale radar images, they discovered powerful tornadoes within the tornado. Chris Weiss is a graduate student on the team.
A lot of tornadoes, some even say the majority of tornadoes, actually have multiple vortices that rotate around a common core.
These multiple vortices have highly concentrated winds that often do the major damage when a tornado strikes. They have never been seen in such detail on radar before. During the 2003 tornado season, Bluestein's team added a new infrared camera to their toolbox. While the radar is measuring rainfall and wind speeds, the new instrument measures temperature and may give us fresh clues in the mystery of tornado formation.
It might be that when there's a strong temperature gradient that we don't get tornado formation, and when there's very, very weak temperature gradient, when the temperature is more uniform, we might be more likely to see a tornado to form. At least that's a hypothesis. We can try to verify that using infrared photography.
Also known as thermal cameras, their modern development dates to the 1950s, and they are more widely known for their military and police uses. But today's cutting-edge cameras show thunderstorms in a rainbow of colors, each representing a different temperature. The clouds, in light blue, are revealed to be warmer than the dark blue sky surrounding them. The heat energy inside the clouds is the fuel that drives the storm.
Up till now, we've only had the ability to look straight down at a thunderstorm with a thermal camera from a satellite, or else straight up from a ground-based instrument or from aircraft. We've never really taken a thermal camera out into the field to look straight at the thunderstorm and try to deduce things about its thermal structure from a human angle.
The Doppler on wheels trucks use a different technique to examine tornado structure. They are deployed in pairs to gather double Doppler information, scanning a storm from two different directions to get a better three-dimensional view. But a brand new Dow unit came online in 2003 using an unusual flat antenna. The goal is speed, trying to improve on the already fast one-minute scans of the older Dow trucks.
What we found is when we're looking at small things and rapidly evolving violent weather, such as tornadoes and tornado genesis, that 1 minute is just too slow.
Current radars scan a volume of sky by sweeping their beams and tilting their dishes on each pass so they measure different slices of a storm with each sweep. The newest Dow can do it 6 times faster.
It sends 6 beams through the sky at the same time instead of just 1. So instead of slicing back and forth 15 times, we can slice through once and get 6, slice back again and get 12, maybe go a third time and get 18, and it only took us 3 swipes. So in about 10 seconds, we can collect an entire 3-dimensional image of the tornado during the birth process.
As good as their instruments are, the storm chasers face a difficult task. Getting their trucks in the right place at the right time to aim their radar dishes at tornadoes is extremely difficult. As a result, science seems a long way from solving the tornado riddle. To understand how tornadoes form, researchers need to see them, from their very beginning to their ends.
Well, the radar doesn't look very good.
In a decade of storm chasing with high-resolution radar, Howard Bluestein has measured many tornadoes, but only one for its entire life cycle.
Before we really feel that we've made a contribution, I think we'll need to have seen at least 5 or 10 such instances.
No matter how well the chasers eventually learn what makes tornadoes form, the violent storms will still touch down in our towns and cities, producing scenes like these. And yet, science has a contribution to make in this realm too, as technology shows us how our homes and workplaces can take the world's strongest winds. You are watching Nature Tech Tornadoes here on the History Channel. Nature Tech Tornadoes here on the History Channel. The science of studying the terrifying winds of tornadoes extends beyond the spectacular storms themselves. Advanced technology also comes into play as researchers measure the incredible destruction left on the ground. This piece of hardware was created because scientists have found that flying debris causes more damage than anything else in a tornado. The device is called the Debris Impact Cannon. It operates at Texas Tech University's Wind Science and Engineering Center in the city of Lubbock. The cannon was designed by research associate Russell Carter and built by the center's technical staff.
The importance of the cannon is to give us the ability to test wall systems to resist the types of debris that you find in tornadoes.
Based on years of studying tornado wreckage, beginning with a tornado that struck Lubbock in 1970, Texas Tech scientists have found the typical flying debris that does the most damage is best represented by a simple 15-foot-long 2x4. Before the first impact cannon was designed in 1983, researchers had no way to simulate the impact of tornado-borne debris in the laboratory. Simple in concept, the cannon is built to extreme precision, using compressed air to fire missiles toward targets at exactly 100 miles per hour, shot after shot. After accounting for weight and drag, this is just the speed predicted for a 2x4 in a 250-mile-per-hour tornado, F4 on the Fujita scale. An amazing high-speed camera shows the action in incredible detail, contributing to the exhaustive analysis that takes place inside the impact lab. For every shot fired by the cannon, the team carefully measures and records the results.
We want to look at how the missile affected the target when it impacted on the impact side, if it perforated the target, how it exited, and what that damage looks like.
In essence, the debris impact cannon is a tornado researcher's tool in the search for the perfect wall, the kind of wall needed for the extra strong safe rooms often built inside new homes in tornado country. The reinforced spaces are designed to help residents survive severe storms. Under scrutiny here is a concrete-filled safe room wall system submitted to Texas Tech for testing by the Royalite Company of Canada. It is undamaged after repeated shots.
If this had been your safe room, you would have been perfectly safe on the other side of this wall.
Although flying debris is responsible for much tornado damage, certainly it all begins with the wings of the storm. A community in the path of a tornado is subject to winds from many directions. The swirling funnel draws air into its updraft from all sides, so that a direct hit is not necessary for major damage to occur. One of the weak points in many houses is the garage, where tornadic winds get a toehold. As open space rooms with light framing, garages are relatively weak and are easily obliterated by tornado winds. And that is where another strand of the technological web comes into play, the wind tunnel. In another laboratory at Texas Tech, Dr. Chris Letchford and his students are studying how builders can design houses to better resist tornadoes. The specialized device used to study the swirling structure of tornadoes looks nothing like the long, narrow tunnels we might expect. To analyze the twisting winds, high-tech becomes low-tech with the lab's tornado simulator, an odd assembly of plywood, plastic, and duct tape.
We're at the beginning of a study of tornadic winds on building structures. When you're at the beginning of a scientific endeavour, typically you need to take risks, and risks cost money. And the best way of dealing with that is at a fairly low-tech level. And so what you'll see is perhaps a little rough around the edges.
The mini tornado is highlighted by a stream of neon-filled bubbles and sawdust injected into the airstream. Otherwise, the whole thing would be invisible.
You can't see wind, you can see what's in the wind. And when you look at a tornado video, you see debris flying around or dust flying around in the core of the vortex. Typically, you don't get to see the actual inside core of a vortex because it's surrounded by lots of debris and dust. So what you see in our simulator is, in fact, the inside core.
Once the testbed winds are generated, researchers carefully wire tiny models with plastic tubes called pressure taps to measure the forces on simulated building walls. High-speed computer readouts translate those wind forces into numbers for scientific study. While elsewhere, a similar kind of research is going on at real-world scale.
It is a specialty of Texas Tech that we focus on full-scale testing, so we use natural wind in full-scale buildings.
This is Werfel, Texas Tech's wind engineering research field laboratory. It is a full-size building that rotates so that any part of it can be pointed into the strong winds that are almost always blowing here, creating what amounts to a natural, real-life wind tunnel.
This is the wind gust that we saw from the wind speed.
Inside is a fortified safe room housing a computer that samples the wind swirling around the building's exterior. The walls are studded with holes on the outside, feeding to plastic tubes on the inside, which channel wind pressure to electronic sensors. It is precisely the same system used in the wind tunnel lab, but on a much larger scale, and leading to information engineers and builders can use directly.
Once you know the pressure coefficient, and that would be used to determine how many screws or nails you need to attach that panel to your roof rafters.
The concrete block safe room is a must. Tornadoes are common here, and if one should ever strike this building, the scientists inside would be saved, and so would the information their sensors are collecting.
If we were to have a tornado come across Werfel, the data that we would collect would be invaluable. Personally, as a researcher, I would not care to be there. I would care to look at the data that was collected afterwards, trying to learn lessons for the future from the damage of the past.
But lessons for the present are critical for tornado survival today.
Oh, Lord. Keep her going, Lord, and let it get north. Let it get high, Lord. Get it off the ground. Get it off the ground, Lord.
After more than a century of terror in which tornadoes took a horrible toll, technology has now given us a fighting chance. You are watching Nature Tech Tornadoes here on the History Channel. Nature Tech Tornadoes here on the History Channel. Van Wert, Ohio is a small city of perhaps 10,000. A place that looks like it puts tradition and history ahead of science and technology. But in Van Wert, Ohio, looks can be deceiving.
Pusher 449, this is you.
Oh, my God.
It's huge.
Engine 3, we're back on fire band. Just reporting. We have a visual on this funnel cloud.
In November 2002, the entire constellation of our most advanced tornado technology came together to save lives in Van Wert. Scott Schaefer was manager of the town's Twinplex movie theater on the day the tornado struck.
Living in Van Wert, we joke around a lot around town that we always get missed by the storm. It always goes around us.
But as the theater's wreckage shows, the storm did not go around Van Wert that day. What happened here became a focal point in a story of Van Wert's close call with death, as a monster tornado roared on a destructive path directly through the community.
I had a feeling that morning that something was going to happen. It was a feeling that was in the air.
Rick McCoy runs the Emergency Management Agency for Van Wert County. The county has been certified under the Weather Service's new Storm Ready program. Certification means Van Wert is making best use of the full technological spectrum. On November 10th, 2002, it all went to work. At 1:40 that Sunday afternoon, McCoy heard his NOAA weather radio broadcast a report. The Storm Prediction Center in Norman, Oklahoma was issuing a severe thunderstorm watch for the Van Wert area. McCoy took that as a cue to go to his control center and keep an eye on the situation. Less than an hour later, things got much worse.
This is David White at the Van Wert County Emergency Management with a special weather statement for all listening amateurs.
At 2:45, Doppler radar at the National Weather Service detected the telltale sign, a severe thunderstorm with strong rotation, the kind of thunderstorm that can produce a tornado. A tornado warning was issued for 3 nearby counties. McCoy knew that Van Wert would be in danger.
I'm requesting spotters at this time. The sheriff in Blackford County reported this storm produced a tornado in Hartford City. Again, I'm requesting spotters at this time.
In the nearby village of Wilshire, in the path of the coming storm, volunteer fireman Dennis Bowen responded. He is part of the well-trained spotter network McCoy dispatched as his first line of tornado defense.
I got to this point and we started looking up at the sky. The clouds started doing a full rotation and there popped down the tornado. Wilshire 449, this is Unit 37. We have a tornado on the ground. I repeat, we have a confirmed tornado on the ground.
Minutes later, the Weather Service issued its tornado warning for Van Wert County itself. It was 3:02 p.m.
When a tornado warning is issued, it means that the tornado is imminent at that point, that it's approaching the area, and my job at that point is to warn the public.
Now, McCoy put his high-tech communication system into action. A key component is a specialized radio receiver called the Informer, placed in all public buildings and many businesses all over the county.
It goes off with an alert or a siren that will activate for about 5 seconds to get your attention. This is the Van Wert County Emergency Management with a special weather statement to nationwide.
At the same time, McCoy set off sirens, technology dating from the Cold War, when they were there to warn against air raids that never came. Now they've been updated for 21st century tornado warnings.
Seek a safe place in a basement. If that is not available, go to the center of your house.
Funnel crowd spotted. Here's to be on Glenmore Road, heading towards Van Wert.
This is the Van Wert County.
McCoy had deployed his spotter network in time. The entire communication system worked without error. As reports came in, he was able to trace the tornado's path with remarkable precision.
They were able to tell me that it was getting larger, and that was very important information that I continuously kept relaying to the public and the National Weather Service.
And just as spotters were equipped with video cameras, so were residents all along the tornado's path. As common as it is, video technology is invaluable in preserving the experience.
It's going up. Come here, look. Real quick. Real quick. Come here, Clay. There's 2 of them.
Oh my gosh.
Come here, you guys. You guys will never see this again, probably.
Oh my gosh.
Sounds like a break.
Oh, it does. Oh my
I can't even hold the camera still.
These remarkable scenes came from a camera once owned by Mark and Cindy Klinger. Transfixed by the approaching tornado, they were compelled to take these pictures. Earlier on the same reel of tape was their life, their home, their daughter McKenna. They never suspected the danger awaiting them.
Speed racer.
Oh, honey, we need to go under or something.
Come on. Okay.
Get in here.
Okay, go. Get underneath. Get underneath.
The tape was removed from the damaged camera that was found in the wreckage of what was once the Klingers' home.
We are in the middle of a tornado at 4224, and the old tile is headed right toward Lincoln Highway.
The tornado surged ahead on its track of destruction through Van Wert. McCoy could see where it was headed, and he knew lives were in jeopardy.
This is Van Wert County Emergency. As the storm was progressing through the county, it became very evident by the spotter reports that this tornado was heading towards the cinemas.
On a Sunday afternoon, McCoy knew the cinemas would be full of children, unaware of the deadly storm's approach. The danger was critical. The theater was equipped with an informer emergency radio. The alarm tone went out, and theater manager Scott Schaefer prepared to act on McCoy's message.
This is the Van Wert County Emergency Management. We have a tornado on the ground, Lincoln Highway, 224, approaching the Twin Cinemas, Van Wert Emergency Management.
I was panicking, I was scared. I guess I've said I was too scared to panic. I don't know if that makes sense, but it's what I feel the best of saying.
Despite his fears, Schaefer and the theater employees got everyone out of the auditoriums and into the central hallway and bathrooms, the safest places in the building to be. In minutes, the tornado was upon them.
I was crouching down in the hallway with like the old school position they teach you, the hands over the head and down between the knees. I didn't have time to stop and think what exactly was going on. I was just hoping we'd make it out of there alive.
The first information that came into my office at the theater was that maybe everyone had lost their lives.
Van Wert's Twin Cinemas took a direct hit. In the auditorium, where children had been sitting, the winds had tossed 2 cars directly into the seats. But thanks to a system that worked, no one here was even injured.
And then as we got information later that everyone there was okay, it was a very wonderful feeling that everyone was able to survive an F4 tornado.
Intelligent use of technology made the difference in this community, whether it was something as complex as Doppler radar or as simple as the sirens. Sirens that Mark and Cindy Klinger heard.
Don't fall down. Yeah, careful.
The Klingers are the couple who videotaped the tornado as it came within yards of their home. They and their daughter McKenna survived, even if their house did not. As the storm approached, they knew what to do, quickly huddling in the crawl space under the floorboards. It was just enough to save their lives.
I just grabbed hold of McKenna and Cindy and just held on tight, and we...
And the noise and the rumble was so loud, I kept screaming to my daughter, "Are you okay?" And she yelled back, "Yes, I'm okay."
It was almost like the house exploded above us.
Months after the tornado, Van Wert was still cleaning up, and it will be a long time before it recovers from the property damage. But property can be replaced. Lives cannot.
Had it not been for the early warning system, the Storm Ready program that we had in place, we do know that we would have had hundreds that probably would have lost their lives in this storm.
Scientists believe that the days when tornadoes killed hundreds of people in a season are unlikely to return, as they pursue their long-sought goal of understanding how tornadoes work, and as the instruments they use become increasingly efficient, we may one day be able to predict them with certainty. At that point, their awesome power will become a spectacle to see, but one that we no longer need to fear.
Next on Tech Tuesday. In the old days, we could see the bad guys, so we developed stuff that could attack. Now, it's a different ballgame. We can't see them, but we know they're there. So we invented stuff that can detect and stop them.
Stop the vehicle!
Military on Terror Tech. Next, only on the History Channel.
A model airplane.
Definitely a beast now with all the concrete that's in it.
It's got a lot of concrete in it?
Oh my goodness, it's more than half full of concrete. There's a slab of concrete in there that's 3.5, 4 feet thick.
What happened, guys?
I was thinking it might be a couple of inches around the inside, but no, it's actually full. So if you calculate that all the way to the bottom of that hopper, that's a slab of concrete.
Just when this myth